So now we're going to talk about how do we actually go about storing these branch history bits in the processor. And this is going to be a brief introduction to associative structures. We're going to see a lot more of these structures when we talk about caches a little later on in the course. So let's talk about keeping the branch prediction data. We said what we want is a table in the processor that keeps track of whether each branch is taken. So we need to be able to check on each branch to see what to do, and we need to be able to update it once the branch is resolved. So that is, if we mispredicted, we want to go in and update it with the correct prediction. So how does this work? Well, we're going to use an associative memory or a content addressable memory, or a CAM. And this is a memory that's a little different than the memories we saw before. Instead of having an address, which tells you where to look in the memory, we're going to put something into the memory and it's going to tell us if it has information about it. So we're going to input the PC of the instruction we're looking at, and the memory is going to tell us what it knows about the PC. So here's our memory. We're going to put in the PC, and the memory is going to check and see, do I know anything about that PC? If it does know something about the PC, then it's going to output some data. It's going to output two things, valid and the prediction bits. So valid tells us, is this a branch that you should pay attention to? And the prediction bits tell you, if it's a branch, what should you do? So this is great, but we have a question. Where does the branch go? So with this information, we can predict if the branch is taken, but we don't know where it's going. Remember, in our MIPS pipeline, we had to put in a special adder that we moved up earlier in the pipeline so we could calculate the address. On modern processors, it's not really practical to calculate this ahead of time, so we want to predict where we're going to go. And the way to do this is we add the branch target, that is the address the branch is going to the table. So now our table here is going to output whether the branch is valid, what the prediction for the branch is, and then where we expect the branch to go. So this is now a branch target buffer, or a BTB. And this is how we're going to predict branches in the processor. So let's talk a little bit about the branch target buffer, or BTB. For each PC in the program, the BTB is going to store if that PC is a branch. So we're going to look in there and say, is this instruction a branch? If the branch is predicted taken or not taken, so that's our prediction. And then the address of the branch if it's taken. So where is this branch going to go if we predict it's taken? We're then going to need to update the BTB when we know what the branch is. So if the branch does what we thought it would do, we want to update the branch predictor to make sure it's really sure that that's the right prediction. And if it didn't do that, we may want to change the branch prediction, so next time we'll predict something different. There's a problem with this, and that's that the BTB is not infinitely big. So it can't hold every branch in the program, and if you have lots of branches, you can't keep them all separate. So this works very well if you're only looking at a few branches, but not so well if you have lots and lots of branches across a whole program. Luckily, most programs concentrate on little small pieces at a time, so this trade-off works really well. As I mentioned earlier, we're going to see a lot more about these associative memories when we get to the lecture on caches. So a question about the BTB and the jump instruction. So what's the benefit of using a branch target buffer for a jump, that is an unconditional jump instruction? Well, it will allow you to determine the branch address earlier. So the branch address needs to be decoded in the instruction decode stage and then used to calculate where the branch is going to go. If we have a BTB, then we can determine the destination of the branch already in the instruction fetch stage. How do we predict whether a jump is taken or not? Well, we know that jumps are always taken, so almost any predictor is going to get jump instructions right, since they don't change. So here's a question. What outputs will you get from the branch target buffer if the branch is not in the table when you get to the PC? Well, in this case, the only output we care about is that valid is going to be 0. If the PC address is not a branch, then valid will be false, so we know it's not a branch, and we ignore the rest of the output from the BTB, because the BTB is only taking care of what are branches. So if it's not a branch, then the BTB says it's not a branch and don't pay attention to me because I don't know what I'm talking about. So if the BTB says it's not a branch, what's the next PC that we load? Well, here we're going to do the standard thing. we're going to go PC plus 4. So the branch target buffer doesn't have an entry for it, so we're going to assume that we go on to the next instruction. If it turns out that that instruction was a branch, then we're going to have to update the branch target buffer with that PC so that next time we'll know it's a branch, and we may have to go in and kill some instructions if we went in the wrong direction.